If you're making long requests to large language models, this video is going to help you to get faster and cheaper responses. Models like Claude Sonnet and Google's Gemini increasingly allow you to add more background information to questions you ask. This means you can input over 100,000 or even over 1 million tokens of background information. While this is useful, the answers can be slow and expensive. For example, a question with 1 million words of background info might take over 30 seconds to process and cost you a few dollars. But if you're reusing the same background information for most of your questions, there's a trick that allows you to increase inference speed by a factor of 2 and save costs by a factor of more than 4. This technique is called context caching, and it allows you to run calculations on your background information once and reuse the results of those calculations in subsequent requests. In this video, I'll talk through the basics of how context caching works, how to use it with Claude and Google Gemini models, and then I'll run you through some of the cost savings you'll make by implementing this technique. So for video overview, I'm going to talk through how context caching works. I'll review attention in transformers, give you an intuitive explanation. I'll explain how these calculations are stored, the calculations and the background info. And I'll talk through what you can cache and what you cannot cache. So where you can make benefit of this technique and where it just won't work. Then I'll go through demo scripts. I'll do demos for Claude and for Google Gemini Flash. It also works with Google Gemini Pro. I don't believe OpenAI have got caching available yet. Perhaps they do some degree of it themselves on the back end, but it's not available via their pricing or as a developer. And I'll go through as well context caching using SGLang, using Llama 3.18b on RunPod. You could also use vLLM. Context caching is something that is fairly widely supported via radix attention, which I'll talk about a bit later. And last of all, I have a slide just on cost and speed comparison. It's actually just cost comparison. We'll see the speed comparisons when we go through the demo scripts. So I'll show you the cost difference between Claude and between Gemini. Actually, I can maybe even just start with that just for a bit of a warm-up. I'll go through this in a bit more detail later. But for example, if you have a setup with 100,000 tokens of input and 500 output tokens, and let's say you make 10 requests, you have the same background information for all 10 requests. This is what it comes out to. If you use caching with Gemini Pro, all of these requests will cost you just under $1, whereas with Claude Sonnet, they'll cost about 67 cents. And then without cache, you've got a factor of about 4 increase in cost, and roughly a factor of about 4 to 5 for Claude Sonnet. So you can see here, definitely a 4x reduction or better in terms of cost if you use this caching technique, provided you are always inputting the same background information, which may be some reference documents or something else, maybe like an extremely long system prompt. I doubt your system prompt would be 100,000 tokens. It's more likely that maybe you have a long system prompt of, worst case, a few thousand tokens plus some background information that you're sending in for every request. So let's get started to understand how context caching works. And to do that, I will explain briefly how attention works in transformers. Actually, I've written here, or I've represented a very simple example of a transformer. And in this transformer, we have the word the, which goes as an input. Let me just increase my screen size. We've the word the, which goes into what's called an embeddings layer. The embeddings layer converts it from a token, the, into an arrow, into a vector. So we have the represented as a vector. And that vector then goes through a language model layer. Now these layers typically have two key parts. They have what's called attention, and they've got multi-layer perceptrons. We're going to focus on attention, so we'll forget about the multi-layer perceptron. So we have this mechanism, which I've yet to describe, that essentially takes the vector meaning of the word the, and it transforms it into another direction and length. So it transforms the vector here to the vector here. And the whole idea of a language model is you want to have a set of embeddings to make vectors, then a layer or multiple layers with attention that will transform the vectors in such a way that the vector, when it gets to the output and is converting through a de-embedding layer, which is the reverse of the embedding, we will get the most likely next token, which here I'm saying is quick. Then what we do is we take the next predicted word and we pull it back to the input, and now we input these two words. So they're quick, and we propagate this through here, to get the next word brown. Then we pull the word brown down and we propagate that through and we get the word fox. Okay, so this is the basic transformer setup. And the key thing that will be important when it comes to caching and storage is that when we calculate the transformed output vector for the word brown, so we have this vector gets transformed to here, the way that this attention layer works is that it's going to calculate this vector y3 here such that it depends on all of the prior inputs. So it's going to depend on x1, x2, and x3. So you can see here how the output that's going to lead to fox depends on all of these prior inputs here. So at the previous step, likewise, we would have y2, which is the output that will be converted to brown, and it depends on these input vectors here, x1 and x2. And this is where the storage comes in, because you can see that when we do a forward pass to calculate the word brown, we're making use of x1 and x2. So we might as well store x1 and x2 so that when we get to the next step of feeding forward to calculate fox, we can just reuse x1 and x2. And this is the whole idea of storage or of caching. You basically want to take stuff that has previously been computed so you can use it in the future and you don't have to rerun through, for example, the embeddings layer here. Now, I've just shown a single layer example of a transformer. In practice, these often have 30 or 70 or 100 repeated layers, transformations that will keep transforming the vectors as you get to the output. Here's one I drew with 2 layers. So you have, in this case, some output from the second attention layer, Z3, and it's going to depend on all of these, and it's going to effectively indirectly depend on all of these here as well, because Y3 will be calculated depending on these, and then Z3 will be calculated depending on these. So effectively, Z3 is kind of a function of all of that past history. So you can imagine this increasing up for multiple layers, and the more layers you have, that means the more things that are useful to store, so that when on the next go round you calculate X4, you've stored, well, let's say Y4, you've stored all of these, and Z4, you've stored all of these here. So you can see that more layers, that means more things we want to store to avoid recomputation, and that means we will want to have a larger cache. Now, you'll have heard of the KV cache. Right here, this is kind of an X cache or a Y cache because I'm storing X's or Y's, but it turns out we don't just store these vectors here. We actually store some derivative forms of those vectors. So let me explain exactly why it's the K and V that we store. So for each vector X, and you can think of a vector X just as maybe X1 right here, we're going to store K and we're going to store V. So what are they? Well, K is what we call the key, and it's computed by multiplying a large matrix K by X, which is that input vector. And the key really is a vector that says, what do I look like? So, I'm Ronan, I've got black hair, I've got a beard. That's what I look like. We also compute a value vector V, which is big V, another matrix that's trainable, times X, the input. So just to clarify here, we're always taking these X's, like this one here, we'll calculate a K and a V. This X here, we'll calculate a K and a V, and we'll do so using the same big K matrix and the same big V matrix. And what the value V says is, how do I affect the next token? I'll explain a bit later how to think about this, but if you imagine you're an early token in a sequence, you're going to have some influence on the next predicted token. You're going to have some say on that, and you can think of the value as what the token wants to say about the next predicted token downstream in the sequence. Now, there's one other quantity we'll calculate, which we actually won't store, and that's called the query, which also is computed by taking a trainable matrix Q. It's just a matrix of constants times X. So again, there's going to be a Q for each of these vectors here. And what the Q does here is it says, who am I looking for? So if I'm at this position, say Y3, I'm going to try and calculate a Q for this vector X3. And that Q is going to say, which of these prior vectors do I want to look at to get information to help me predict Y3? That's essentially what Q is doing. And the reason why you don't store Q is because once you have already computed everything here, you're always only looking at the next token. So you just need a Q for this position to look backwards. You don't care that you had at the previous step, maybe you were querying here. So you're using a Q here on the X2. Once you get to X3, you don't care what the previous Q was at this position. because you're now querying at this position, but you do care about what these positions look like, which is the K vector, and you do care what they have to say about the next prediction token, which is the V vector. So yeah, this is how you store the meaning kind of vector X. You actually store transformed versions, which are the key, what do I look like, and value V, how do I affect the next token. So here we have a different the same representation, but I've just written in here inside the attention layer, I've written in, okay, I'm going to store the K1 and V1 from this X1 vector, and I'm going to store the K2 and V2 from this vector, and Y3, it's going to be a function here of these Ks and Vs, which themselves are constants, trainable constants, multiplied by the input vectors X1 and X2. So this is why when we say we store the KV cache, this is what we're storing. We're storing these representations of the input vector, and we're doing this at every single layer. I'm just showing one layer here. I'm getting to the end here, but just to give you an intuitive explanation, think about this phrase here, 1 + 1 is, and we're trying to predict the next token here, which should be 2. So let's say we're trying to predict this token. So let's go through the steps for doing that with attention. First, we have the query. So we say the query for is, because we're going to run a query at this position to predict the next position. The query is going to be something like, I'm looking for numbers. So I'm looking behind me here to see if there are any numbers. The key, and each one of these words will have a key. So there'll be a key for 1, a key for plus, a key for 1, a key for is. So the key for 1, could be this one or this one, is going to say something like, oh, I'm a number. So this position here is saying, I'm looking for a number. And then these earlier positions are saying, oh, I am a number. And that's how you have the query that's going to effectively search for the key. And that's mathematically done by a dot product. We're basically saying, okay, I'm looking for numbers. That's the Q here. The dot product is going to be high with any of the tokens that say I am a number. So it's going to be a high dot product with 1 and 1 here. And when that dot product is high, we're going to multiply that by whatever the token is trying to say about the next prediction. In this case, maybe your next token should be 2. And so that's kind of an intuitive explanation of how you calculate what each prior token has to say about your next prediction. To recap, you have this query, you're querying who to listen to. You have K, which is saying who I am. It helps identify through the dot product which token to listen to. And then you multiply that by what each prior token has to say about what it thinks the next token is going to be. So here we have it all, attention in transformers. You have some next token prediction. That's a function of the prior KV cache. And so therefore, when you are doing a forward pass, it's beneficial when you're calculating Brown to save up these K1s, KV1s, and these K2, KV2s, so that when you go forward for Fox, you're able to just reuse the calculated numbers rather than recalculate. So this brings us to 2 types of caching or storage. And caching and storage, that basically means the same thing. And the 2 types are the standard type, which is what I've kind of just described. Here, we're storing KV for the same sequence. So if we have a sequence that says the quick and we're predicting the next token, we will store the K and the V cache for the and quick, so we can reuse it for the and quick when we get to predict the next token that comes after Brown. So this is caching within the same sequence, and this is pretty standard. If you look at any inference library, vLLM, TGI, SGLang, they will always be caching the KV from the prior tokens so that they're not being recalculated. And that's going to save on computation, and it's going to save on time because you're avoiding recalculating. But the other type of caching, which is important for this video, is long-term caching. And this is where you're caching not just for the same sequence you're generating, but also for later sequences. And where this makes sense is, let's say you have a prompt with a lot of background information. It could be a novel, and you have a question then or a command saying, please summarize. You can use that. You can use the cache for background information for a future prompt where you have the same background information, but a new question that says, who wrote this? And you'll be able to share the KV values for all of this background information to save you all of that computation. So what this means is you have a server and you store the KV cache because somebody makes a request, but actually you keep in memory those K and Vs, and you reuse them when the next request comes to the server, and it's going to save you doing recomputations for that background information. So here's where you can use KV cache. It's what I just described. You have the background information and then you have the question. But where you cannot use caching either between different sequences is if you put the question first and then you put the background information. And that's because if you change something at the start of the sequence, that information is going to propagate forward in all of these calculations and change the numbers that you're going to store. So you cannot use caching if you are going to change something at the start. And the implication is it's going to be beneficial, kind of irrespective of performance, which is something else to think about. You're going to be better off lumping all of the background information right up front in your prompt because you want to keep that constant for every query. So you can then only change the very last part, which allows you to cache the entirety of your context that you're feeding into the language model. So yeah, that's why it's important to know what you can cache and what you can't cache. So why is KV caching good? Well, it's good because you save time because you're not recalculating those Ks and Vs at every layer. And you save money because basically you're paying for flops. A flop is a floating point operation per second. And you want to save flops because that's ultimately what you're paying for when you're renting a GPU. Now, why is KV caching bad? So why then is KV caching bad? Well, you need to store the values of K and V, and you need to store them deep in the GPU in VRAM, which is expensive. It's not cheap like storing to an S3 bucket or to disk. The values need to be available for computations in the GPU at short notice. So this means you have an added cost of storage, but you have a saving of compute. And that's why when you look at the pricing, which we will later, you'll see that there is a cost charged for storing, or at least for writing to that storage in the case of Gemini and Claude respectively. So that brings us to the demo part, and I'm going to demo three things. First, I'll show you how to do KV caching with Claude and what kind of speed up you get. Then I'll show you with Google Gemini Flash. It works with Pro as well. And then I'll show you how this works with SGLang, which is an open source inference package that you can use if you deploy on RunPod or on vLLM or some other hosted service, or indeed you could run it on a GPU if you have one at home yourself. Last of all, I'll go back through that cost comparison. So I'm going to work out of the advanced inference repository. This is a paid repo that you can get lifetime access to. I'll describe the scripts in detail though, so really if you don't have the funds to buy access just yet, you should be able to follow along by building it out yourself. I'm going to work out of the API calls folder, which now has quite a few different options here for inference, different tools like doing RAG or regest tests or speed tests. We're going to focus here on context caching, and we're going to look at a few scripts. Let me increase my screen size. Claude cache, Gemini cache, SGLang cache, and I'll quickly take a look at toy cache, which is just a toy model I've built with PyTorch. There's also a script here for Phi 3.5 cache. This shows how caching used within the same sequence works, but not caching from one sequence for future sequences. So I'm going to open this up in Cursor now instead of VS Code. I'll move into the API calls folder, install the requirements, and then I'm going to move into the context caching folder and start to run some of these scripts. So here I am, and I've got a terminal open here. Let me just open up a fresh terminal, and I'm going to just quickly CD into API calls, and I've created a virtual environment that's called API env. So I'm going to do source API env bin activate, and I'm going to CD into cache, context cache, and I need to check what that's called. So context caching. Okay, so let's start with the Claude model here. And I'm starting off by loading Claude and my API key for Anthropic, which will initialize a client that I'm going to use to make chat completion requests. Now I've set up this script so it will parse in the context length that I pass. My default is 400,000 characters, not tokens or words. characters. So that's about 100,000 words. And now I'm going to define my chat completion request for Anthropic. And quite simply, I'm going to pass in a context, which is going to be a long context that we'll define later, and then a question. And you will see here that I have to add in these extra headers to do the caching, Anthropic beta prompt caching 240731. So that's the first difference to what I do normally. And there's a second difference to what I do normally. This is all standard. I'm using streaming to stream out each token one by one. I want to do that so I can see the time to first token, because that's where we save time on caching. It's specifically the time to the first token because we skip a lot of the pre-calculation that would normally be there without caching. So basically with context caching, once the first token arrives, it's going to take you the same time, more or less, as if you weren't using inter-sequence context caching. But it's the time to first token that really gets reduced by using this technique. So all of this here, I think, is fairly standard. I'm just measuring the total time, the time to first token, and I'm going to print out some information on the cache read input tokens and also the cache creation tokens, which I'll talk through when it's shown down below. Now, let me just go up here and check, because I overlooked one extra thing. The second thing here that needs to be added is cache control. So anything you want to cache, which in this case here is the context, you've got to put in this parameter cache control, and you want to set the type here to ephemeral. In the future, there might be other options, but I think this is the only option right now. And I think the standard caching time is 10 minutes. So basically you'll get caching for any requests that are made within 10 minutes of this. After that, you'll have to set up a new cache again. By the way, the cache is set up automatically in Claude once you make the first request, and then for subsequent requests, it's going to automatically read from that cache. So let's go down here. I'm going to open up a text file called berkshire23.txt. You can take a look here. It's just a Berkshire Hathaway meeting that I've extracted the transcript from. And I'm going to check the modified length, which should be a length of 400,000 as default characters. And there's one more trick I'm going to do here. So you can see I'm going to make 3 different calls. On the first call, the caching should happen. And then for the 2 later calls, we should see reduced time to first token. But I'm adding in this unique ID right at the start of my first request. And that's basically to effectively move to a new cache. So remember, if you change something right at the start, you're not able to reuse the cache for anything afterwards because all of that is downstream. So it's like basically throwing away the cache that you had. So what I do when I run the script is I want to start with a new background information, and I'm making it new by adding in a unique token at the start. And then I'm going to run that 3 times and see what happens. So let's go with Python Claude cache.py, and we're running here, and we have an invalid API key. And that is simply because I need to add my API key and the model name within my .env file. So there we go. The first request took 9.36 seconds to first token and 12 seconds in total. So about 3 seconds for the rest of the prompt. And the next, you can see here the cache, by the way, is 84,000 tokens. And request 2 takes 5 seconds, and it takes only 2 seconds for time to first token. So you can see we've reduced the inference time by a factor of about 2, but the time for the remaining tokens remains at about 3 seconds. So it's about the same. And then just to verify a third request here, total time is 6 seconds, 3 seconds for first token. So about 3 seconds, 3.5 for the remaining tokens. But you can see the time to first token is cut down to about 2 to 3 seconds from 12 seconds. So that's a quick demo of the Claude cache. Next up, we're going to try the Gemini model. So we'll head to Gemini cache. And just a reminder to update your environment variables so that you can have the API key and also the model. And I'm going to use Gemini Flash here. But there are a few changes I want to highlight. The setup is a bit different than with Claude. With Claude, you put in a different header, you put in the ephemeral cache, and that will automatically create a cache when you make the first request and reuse it if the cache is already there. With Gemini, it's a bit different. You have to actually send a request to set up the cache. So like Claude, we load the API key, we load a client here and configure it. we're going to use the same default length of 400,000 characters. But now there's a function here called create cached model. So here it will take in some context, and it's going to then set up a cache in Gemini. First, it's going to upload actually that temporary file name, which is basically created using the context. And then it's going to process that cache. And once it's all uploaded, it's going to be ready for us to create, or once the file is uploaded, once the file is uploaded, it's going to allow us to create a cache using that file. So that's what we have here. It's a cache with a system instruction and with display name, and then the file as the contents here. And you can see we can set how long this cache is going to live for, so that if we make requests within the next 5 minutes, that cache is going to be reused. Next, using that cache, we can define a model using the GenAI library, and we're going to create the model using the cached content. So this is how you do it with Gemini. You first upload the file, you create a cache, and then you're able to set a model using that cached content. So the idea here now is to have a create chat completion request Gemini, where we pass in the context and the question, and we'll call this create cached model. But if we've already run that same function with the same context, it's basically going to skip creating this cache thanks to this LRU cache decorator, and just return the model that will be using the cached context. And then we'll proceed with the streaming, see each token come out, measure the time to first token, measure the total time. And again, we're using the same Berkshire file here. And again, we're also using this unique ID at the start. And that allows me to basically create a new cache because it's going to be different based on the unique ID every time I run the script. So let's run Python Gemini cache.py. And the first test is uncached, which means it should be creating a cache and then running inference. So here for the first request, we have a total time of 12 seconds with a 9.5 second time to first token. And for the second request, we've got 9 seconds with a 3 second time to first token. So that's 3 instead of 9. And then the third one, we've got a 1.87 instead of 9. So basically our time to first token went from 9 down to 3, and our total time went from about 12 down to 8.5. So yeah, more than a 2x improvement in time to first token, and not quite a 2x improvement in overall generation time for this request. So that's the Gemini example. And the next one I'll show you is SGLang. This is where you're inferencing a custom model on a service like, say, RunPod. If you go to the README and you scroll down for SGLang, you can find this one-click template. It's also, I think, in the one-click LLMs public repository on GitHub under Trelis Research. And this will bring you to a view where you can select the GPU. I've just selected the A40, it's cheapest, and then you can run this model here with one click. Now I've set this up a little bit earlier, so I'm going to go to that pod. I'm going to check the logs, and the server is fired up and ready to roll. So I'm just going to copy that pod ID, head back to cursor. I'll go to my environment file and set up my RunPod proxy ID. Just to give you a sense, what you need to input is this URL for RunPod, but you want to swap in your new pod ID, and you're going to want to put in the model name. The model we're using it's actually not Neural Magic, it's a new research model, which you can check right here. It's basically an ungated version of the MetaLlama model, new research MetaLlama 3.1 8B instruct. So I'm going to set that up in my environment variables. Give me a second. All right, that's set up now. And a quick look through this script. So the thing with SGLang is you're now hitting a server that you control because you're running the server. And this means it can be automated more easily, or rather the context caching can be automated more easily, because you can probably assume that if the same user is using the server, there will be a lot of reused cache. And so there's a program, I think it's based on Radix attention, where it will automatically decide to cache queries. So any request you send in, it's going to pretty much cache that query, and it's going to cache many queries and then start to dump out some of the oldest ones, basically. So there'll constantly be a cache that's maintained, and it will be maintained based on usage, and that will kind of automatically allow you to get speed up. So there's nothing we need to do in terms of setup. we just set up an OpenAI client. We're going to have the input of 400,000 tokens, but there are no special parameters here when I'm setting up the streaming because it's happening automatically on the server side. We're doing everything else the same though. I'm setting up a unique ID to make sure that every time I run this, we're going to get the same thing. So, or rather, we're going to start a new cache. That's the key thing. If I don't put in the unique ID, I would be using a cache from when I ran this before the video, and that would give me speed up already on the first request because it would be using the old cache. So I need to have like a fresh cache every time I run this script. So Python SGLang cache.py, and I've added in a little warm-up call, which is just with a short number of tokens. And this looks like I'm not connecting, so let me check my parameters. Yeah, so one problem I remember is that if you're using an A40, you're not going to fit that long of a context. So just reduce it to something small. Maybe like if you go for something like 40,000 characters, that's like 10,000 tokens in length. You can probably try something out like that. Now, do wait until your server is back up and running. Okay, so we're up and running again. And let's just go with something really small. So we're running the first test here. And yeah, you can see the time to first token is 0.81 seconds. And because it will have cached then that start, we're down to 0.2 seconds on the next request. And on the subsequent request, we're down to 0.2 seconds again. So yeah, this is pretty much SGLang. It's a very short time to first token because I'm using a short context length, but you can see that the caching does allow you to cut down on that time to first token, which translates into more throughput, which means that you would need less servers to serve the same amount of requests, which translates into cost savings. And that brings me to the end of those 3 demo scripts for Claude, Google, SGLang. I wouldn't be surprised if OpenAI releases context caching at some point. Maybe they'll wait till their next range of models. In any case, their models only go to about 100,000 in context length. So it becomes more valuable, particularly for something like Gemini, where you can go up to 1 million or even 1.5 million for Gemini Pro. Then your context caching really matters if you're putting in the same context to all your requests. Now, just to look back at that slide we have on cost comparison, I just want to go through the pricing here and show the difference in how Google are doing it and how Anthropic is doing it. So let's just open that up. And let's also open up the Anthropic pricing link here. By the way, I'll put the slides down below if you want to check out a link to them. So with Gemini Flash and Pro, there is pricing that is in terms of input tokens and output tokens, but basically they charge less for your input tokens, about a factor of 4 less if you're using caching. However, to use caching, you have to pay $1 per million tokens per hour. So that's how much it costs to cache. But yeah, I'm not quite sure if that's just one off. If you store the same million for an hour, that's like $1. That's what I read that to mean. And that means that it's quite a small cost really for storage, and it's definitely going to be worth doing caching if you're going to be sending in a lot of requests. Now, the next one here is Anthropic, and they price it a little bit differently. They do give an even larger discount on the prompt caching. So your tokens go from 3 per million tokens of input down to 0.3. So a factor of 10 difference if you're using caching. However, they charge for writing to the cache, which is $3.75. And you are storing the cache right now for 5 minutes, although I think you can figure that to be longer. So anyway, this looks like it'll probably evolve over time, and they might end up charging like Google for storage time, which kind of makes sense if you are taking up storage over a period of time. But again, you can see there's a pretty significant drop in cost when you move to caching. So when you put those numbers together, and to do so for Gemini Pro, you're basically multiplying 10 requests by 100,000 tokens of input. So that's 1 million tokens multiplied by their price for using the cache tokens, and that's coming out to 87 cents. And then you're doing the same for Claude Sonnet, but you have to add in the cost of that initial write to cache, and that's what's giving you 67.5 cents for this specific setup of 10 requests. And that's the roundup for context caching, particularly useful and recommended if you're over 300,000 tokens of input. Definitely if you're using the Gemini Pro model, which is very expensive, although it caters for very long contexts. I've also put a link to trelis.com/advanced inference, where you can get lifetime access to all of the scripts in the advanced inference repo, or I've put a link if you just want to buy the scripts from today. Let me know of your questions or comments down below. Cheers, folks.